All right. Welcome everyone to join the integration week of our monthly development cycle for the categorical DQN algorithm. This meeting is sort of to wrap up the development on the C51 and to look forward to a new monthly development cycle. So before we talk about what we're going to do for the next monthly development cycle, I'm just going to kind of go over the integration that I've done with C51, some interesting results when I try to essentially reproduce the results reported by the categorical DQN paper. So the first thing is reproduction is difficult, as always, and I did a couple of implementations, but they don't exactly reproduce the results reported by the categorical distribution, categorical DQN paper. In particular, C51 is reported to perform very well in breakout. And let's take a look. So in the breakout environment, they reported to have I believe this is mean score. Actually, they probably mentioned somewhere, but they are able to reach around 700 as sort of the mean score, and DQN is able to reach around 355. For our reproduction, both C51 and DQN wasn't able to reach nearly as high of a score. So this is kind of the results that I have for breakout. I sort of use breakout as the game that I'm optimizing over, because breakout is in a way very difficult. Because as the game goes on, the problem becomes harder and harder, and the ball bounces at a significantly faster speed, makes it harder for the agent to learn the behavior. And there was some issues during the reproduction. In particular, I fixed a bug. I realized that. So this is a file that works for all 4 environments that I tested, but except for Pawn. And I realized that when I was calculating the target PMFs, I'm actually using the Q network instead of using the target network. And as a result, Palm becomes this sort of environment that the agent doesn't learn anything at all. You can see the negative 21 is essentially the results of that particular file. And after fixing that error, meaning to generate the target PMFs using the target network instead of the Q network, then the agent is able to learn, which are the sort of brown lines over here, is able to learn slightly faster than DQN, arguably. However, they still could not reproduce sort of the results by the categorical DQN paper. As you can see, C51 learns a little faster than DQN, but they kind of converge over here around 300, and that's half, not even half of the score reported by the C51 paper. It is interesting to note, though, that this 51 algorithm, there's one particular run that got really lucky and reaches over 800 scores. It's a little interesting, but there's still some work. Excuse me, still some work to be done. In particular, I just started some experiments turning off the gradient norm clipping, and that seems to be a technique that is not being implemented in DQN-related code base. It's only used for actor-critic algorithms. So specifically, it's this line, the neural network.utils.clip norm, and then you clip the gradient of the parameters of the Q network so that their maximum distance is within 0.5 norm of the parameter, something like that. But its essential idea is to make sure the gradient doesn't blow up too much, and that's the run that I'm currently spinning up, and I'm hoping to get results within a day or two. Um, and also, I did some improvement over the visualization so that instead of displaying the atoms, now it actually shows you the return distribution, and the frame rate is also adjusted. So now it kind of looks like this. Let me see if I can download this. So in x-axis, it's a return distribution. So it's especially in Atari games. I don't think there are any negative rewards. Actually, that's not true. For pawn, there are negative rewards. You lose you get a negative reward if you lose a game. But for a lot of the Atari games, there's no such thing. And as you can see, um, when the agent is about to fail, it's highly likely that executing this green action, which I believe is going right, it's going to result in a zero return, meaning the game will terminate. So it shows that it's better to execute the. Let's see if I can find a specific example. It's just there. Yeah, so this would be an example, right, where it shows that the agent really should be executing uh, the red action, which I believe is going right. Um, and executing green action would mean sort of, according to the neural network, would result in the game being terminated. So the visualization is very cool. I'm just kind of very puzzled by why I wasn't able to reproduce the results reported by the paper. Tried a lot of things. I used a lot of the default parameters from the distributional RL paper, including an epsilon parameter for the atom optimizer, but it just wasn't working as well. But now I'm experimenting to take out the gradient norm clipping, hoping that maybe it can do something. So that's about what I have for the Atari. For the C51 reproduction, does anyone have any questions or comments?
Just checking, but for the breakout, I guess you have removed the environment and on lost life or something like that.
Right. So, so right now, we do use episodic life return. Is that the one you're talking about?
Yes, that one.
Yeah.
If the agent loses a life, can it still continue?
Yes, it can. And we're going to accumulate the reward until the all of the lives are truly lost.
But even despite that, it does not reach the high score of.
It does not. Yeah, that's exactly
How
right.
much was it again? 4,000.
For pawn, the results that I was able to reproduce is around
Breakout.
Yeah, breakout. The score that I was able to reproduce is close to 300, but in some of the paper reported they're able to reach something much higher, like 700 for C51 and around 400 for DQN.
Yes.
And if you look at it. Uh, If you look at a code from dopamine, what you will find is that for DQN methods, they don't use the gradient norm clipping. That's why I'm experimenting with not using the gradient norm clipping, because I think maybe it would have something to do with the performance having this sort of bottleneck.
We somehow doubt that, but yeah, let's see.
Yeah, and it's difficult to reproduce. Sometimes. And I would say another thing is that the distribution RL paper, there's some details that they don't really tell you. For example, what's the epsilon schedule, right? It says to use epsilon greedy exploration, but it doesn't tell you exactly what's that. what's the schedule that you use to decrease the epsilon. So they only say that we're using epsilon equal to 0.01 for better performance, but again, they don't tell you how long does the epsilon takes from going 1 to 0.01. And I was able to find something in dopamine baseline data where they actually show you some of the important metrics for the papers reported. So I would imagine they actually talked to the people who wrote the paper and asked them for the hyperparameters. So if we take a look at the paper over here, yeah, so over here they say specifically we set epsilon equal to 0.01, but it doesn't tell you how long does it take for the epsilon to go to 0.01. But over here, they essentially spell out that it takes about 1 million time steps for the epsilon to go to 0.01. And also they have different minimum history to start learning as well in C51. This is also another detail that is not being mentioned by the paper, and the paper also doesn't mention the use of target network, right? Uh, Actually, they do. Sorry, the rest of our training regimes matches the DQM paper, including the use of target network. Yeah, so I guess that makes a lot of sense. And they don't really tell you the target network frequency, I suppose. Uh, well, the point is, at the repo over here, they kind of give you some important information about the parameters that are being set, and now I'm setting the parameters to be these parameters, my parameters to be these parameters, and also taken out the maximum gradient norm clipping, and to determine if that's going to help the agent. But yeah, any any thoughts?
I don't think they used the gradient clipping even in the original DQN paper.
I don't think so too. Yeah,
They used reward clipping, but I don't think.
you're absolutely right. Yeah, so that's something that we can modify for the DQN as well, because a gradient clipping might not be such a great idea. Yeah, so that's for that. Let me think. What else? Yeah, does anyone have any more questions on DQN or C51 before we move on to sort of talk about the next monthly development cycle? Okay. So maybe I can start talking about some of my plans for the next development cycle. Um, so what I think would be helpful is for us to try to reproduce the Atari results for PPO and A2C, and that would involve in using potentially involves the use of the vector environments. But I was hoping to do it in a cleaner way than the OpenAI baseline, how they do it. So a naive application of the current A2C, right? If I just copy this A2C file and use the Atari wrappers and just sort of run based on it using the same convolutional neural network and layers, it doesn't work. Specifically, the entropy just goes to 0 right off the bat for some reason. So I don't know what's going on. I have some thoughts about what could be the reason, but overall, it's sort of a mystery for now. And so that's something that I really hope to do, because A2C and DQN are some of the methods that are shown to run a lot faster than, um, well, in a way, sometimes faster than DQN, but it doesn't require nearly as much memory requirements, specifically because it doesn't require the 1 million replay size. And I was hoping to, for the benchmark, I was hoping to sort of divide this into 3 sections. The first sort of similar as to how they benchmark the performance in the autonomous learning library, where you have the benchmark for Atari Games, and then you have the benchmark for continuous action domains such as PyBullet, and then have another section for just classical controls such as Carpal, Taxi V2, or Luna Lander. So that we have an idea of the agent's performance in all of the games at one place. And the legends can be changed as well to make them to read a little more, to be a little more user-friendly, stuff like that. But yeah, that's kind of my plan, because right now for Pawn, as an example, we only have DQN and C51, when in actuality some of the algorithms such as A2C and PPO are known to be able to work in those domains as well. So what do you guys think?
No, I think it's a really great idea to introduce the convolutional neural network with PPO, and A2C. Yeah, it's really very good idea.
Mm-hmm. Nice. Well, yeah. There is also kind of a, I guess, personal reason, because my research works with real-time strategy games, and when you deal with strategy games, because they have this sort of spatial features, it is also usually preferred to use a convolutional neural network. And the choice of algorithm that I'm using is PPL, and it has worked pretty well, actually. I can kind of show you maybe some examples. But I was hoping that maybe if I, apply PPO on Atari, I'll be able to understand something more about how to use convolutional neural network and improve the training efficiency. And that's something that I'm very interested in. So let me see if I can find the run. There is some very interesting runs. So maybe this. Yeah, so this is an interesting run, right? So essentially, agent on the top left is my agent. I train it to collect minerals, and then it's supposed to march over the enemy base and destroy them. And the reward is very volatile. But in this settings, I am using the convolutional neural network as shown over here. But yeah, I was hoping to sort of do the same thing for Atari, because maybe it doesn't work right off the bat with Atari, and I can learn why. And maybe that why will help me to build better, to sort of improve the performance of this algorithm for my research. And in a way, talking about the application of Atari, you have to sort of think about how you handle the episode. And I think that's a very tricky thing, because usually in A2C algorithms, actor critic algorithms, what they sometimes assume is that you have a fixed episode length, such as 200. So in a lot of the pseudocode that we see nowadays, like for example, for my A2C as an example, I set up an episode length. So essentially, first step in the episode length, I copy the values and the observation and calculate the log probability, and essentially use that to update the agent. However, in Atari, this is much more difficult, because the horizon, the episode length, is much larger. In particular, I think that the episode length of any Atari games is 400,000. And if we were to naively just kind of apply the A2C code right here to Atari Games, that's going to be very challenging because right off the bat, you're allocating a lot of arrays of 400,000. And that could be very memory costly. And the approach that the OpenAI baselines does is to use the vector environment. And the vector environment is especially interesting because it handles the environment reset for you. So what that means, I was hoping to kind of show you an example because I think it's definitely one of the most sort of interesting things. So OpenAI baselines, they have their own vector environment wrapper, but I don't think that's going to be the vector imp that I'm going to be using because I think it's probably cleaner to use a vector environment from Gym. And I don't think the vector environment in OpenAI does anything more in a way. So let's take a look real quick. There are some documentations, but I think it's easier to find out. Yeah, there's an initial pull request that shows the example of kind of how to use it. Yeah, this would be an example. I think this would be a much cleaner API than the baselines API, which is somewhere over here. Common vector environment, vector env. There's a lot of things written out. I mean, even though the Gym environment is probably doing the same thing, but under the hood. But I think it's much cleaner if we just kind of use the wrapper provided by Gym directly. So this would be kind of what it means. Now, observation will look like this, right? And then when you do the stepping, you can do m dot step, m dot action space dot sample, and so the interesting thing, right? Notice the arrays corresponding to the termination condition. So right now it just false, false, and false, but it's only after a few runs that one of them is going to be true because in the carpal environment, the episode is going to terminate. So over here, notice one of the episode terminates, right? Then you can continue to keep running this, and then some other environment terminate. But it always just continue to execute, and there's no point that you're going to manually call the environment dot reset function. And because of that, OpenAI baselines have sort of two arguments when you run the algorithm, such as PPO. I don't think it's going to make any difference for the DQM based methods, but it makes a lot of assumptions for active critic methods. So over here, what you can see is that you have this argument that says number of environments. And where can I see? The number of environments is actually not specified over here, but you do have this argument that says n steps. Which by default, the batch size is the n steps times the n n's. So going back to our example, we have 5 m's, and then if we say, something like for I in range n steps equal to 5, this would be what it means. Okay, and essentially, they just kind of collect data based on the 5 m's and 5 steps, and then they sort of bootstrap the values if the environment is done. If the environment is not finished, otherwise they just kind of use the reward as it is, and then they handle it from there. But from our perspective, sorry, let me think about maybe what is a better way to put this. So as you can see, one of the assumption that the vector environment makes is that your states, you don't really start at a fixed initial state as it would have been for DQM based methods. Except if you use the episodic life wrapper, in which case then the initial state could be the terminal state of your last life. And in a way, that's how I think about the vector env, because you're essentially saying, instead of using the episodic life, I'm saying my episodic life is always going to be length 5. It's going to be the length of the n steps. And then you start from there. Does that make sense?
Kind of.
Okay. Well, think about this, right? Perhaps it's helpful if we look at a video. And for simplicity, let's just consider nm's just equal to 1. That's I don't want to use pawn because pawn doesn't use the episodic life environment. All right, so let's use this as an example. So over here, you can see you have 5 lives, right? And this is your initial state. You start with all of the blocks over here. That's your initial state. And then you start running the game. And then you have actions, you have rewards, blah, blah, blah. This is actually the first time I'm waiting for the agent to die. Okay, so now the first life is lost, right? That's why you see there's a 4 over here. So this state becomes the initial state for the agent again. So the agent treats whatever goes on before this as a terminal state, and then the episode kind of finishes for the agent. And then this is a entirely new episode that starts over here, and this is the initial state. Does that make sense?
I see.
Okay. And
what wrapper does this?
It's an episodic return wrapper. So just open Steam. Okay. So if you look at the code base, specifically C51 Atari or DQN Atari, what you're going to find over here is an episodic life environment. So let me zoom in to this maybe a little bit. And notice it's taking the original environment, saying I get the observation, reward, done, and so forth. And then it sets the was real done equal to the done. But then it's saying if I still have lives, then the done is going to be false. If lives equal to the actual lives, if lives is greater than 0, oh, I see. So it uses the self.lives to right. So if I lose a life, essentially, then the done will be equal to true, right? Does that make more sense, Rosalind?
So far, so good.
Okay. So in a way, it's kind of changing the problem because your initial state becomes different based on when you lose your life, right? So that's how the episode. Beg your pardon?
It's probably good for neural networks, right?
Yeah, it's like saying you don't have to run all the way until finish. You can sort of start in the beginning. But yeah, so that's one of the optimizations they've done. And if you think about how vector env would sort of come into this picture, if we're considering we're only using one environment, and let's say steps equal to 5, So similarly, this would be the initial state, right? And then you run for 1 time step, 2 time step, 3 time step, 4 time step, 5 time step, done. So that would be considered as a time limit in a way for the agent. And then you get a state, you get the rewards, and then you get the actions, and then you bootstrap the rewards based on that. Because it's not truly done, you use a value function to get the future reward and append it to your reward to do all the calculations for the advantages and so forth. And now at the next state, this becomes the initial state for the agent at the next episode. And then you do it again: 1 time step, 2 time step, 3 time step, 4 time step, 5 time step, and then done. And then you bootstrap the reward again. So that's essentially the vector M does. Do you see how it in a way is similar to the episode again? Because you're changing the initial state based on sort of how you run the environment.
In this case, even when the initial state is changed, what difference does it make?
I think
Really see.
I think the difference is that in a way you could not, maybe it's not possible for you. Maybe given a single episode, it becomes more difficult to for the agents to realize some actions have this is sort of continuous, not in the sense that I'm going to generate a continuous actions in real values, but some actions are sequential because you're cutting off the episode early. And some actions, let's say if you were to execute a task that really should span for 10 time steps, and then you get a reward after that, then using this vector M could have surprising consequences, right? Because then you execute 5 actions, and then your episode finishes, and then you get 0 reward, and then for the next time step you get another 5 actions, and then you get the reward. But then the neural network doesn't attribute the reward to all of the 10 actions, but rather it'll only attribute the reward for the last 5 actions, intuitively speaking. Does that make sense?
Even if that was the case, I mean, it's already the case since the agent only have like 4 time steps.
And maybe that's not something bad. It just it may not necessarily be something bad. It's just an observation that is characteristics of the vector M.
I would say it's just depend on the representation it learned, so it should not matter if the initial state is like the real initial state or not. Because even on the observation you are showing right now,
Mm-hmm.
I would say since the agent already learned on the previous episode how it managed to get here, the representation should still correlate with that of the past, so it can still manage to finish the game.
Yeah, that makes perfect sense, right? Because reinforcement learning assumes states are Markov. So your current state is an encoding of all of the previous states. So given any states, you really should be able to play from there, right? Yeah.
Yes, I see what you're saying.
Right. So yeah, it's just an observation. It changes the problem because your initial state becomes different. And I think that's one of the nuance that's maybe being underappreciated, and I think it could have important impacts.
I think what you're saying would be more relevant if we were using some recurrent neural network. But so far, with the only feed forward type of networks we're using, I don't think that even if the reward that was supposed to come out after 10 steps is only received like in the second episode only after 5 steps, how does it make its way back to the first of the series of 10 time steps if we're not using recurrent neural networks? I don't think that will even happen. So
Okay, so maybe let me provide a perspective on why vector environment, in a way, not only it changes the problem, um, but also it has this significant impact on how we would use it, and that's on Atari Games. So the Atari Games has long could have very long horizon, right? Have 400,000. And if you recall how we do the PPO2 implementation, we assume the batch size, right, of 2048. And that would mean that if we were to apply PPO2 directly to sort of this environment, what's going to happen is that the agent could never get over 2,000 time steps or more.
Okay.
Yeah, obviously we could set a larger batch size, but that would be very memory costly. However, using the vector M, then it wouldn't be a problem because you're essentially running chunks of episodes. If an episode is 400,000 length, you're running the first 2,000 and then the second 2,000, the third 2,000 until it actually finishes. So in a way, it can be think of as this sort of memory optimization as well.
Okay.
Yeah, it is quite interesting, right? So yeah, so I think we still sort of handle the once the environment goes for n steps, we still do all these to bootstrap the values and calculate the advantages, but we do that for each of the environment, and if we want to use the existing implementation, we just sort of append them together, and that'll directly apply. So yeah, so that might be something that we need to implement for Atari Games because, sorry, 1 second, because it becomes important because we can't really just allocate 400,000 memory for actions or the dones or observations. It becomes very memory expensive, and it makes much more sense to do the vector M. So that's why I think we should do that, even though it introduces extra complexities.
So basically, what you're saying is for each call to the vector environment, say if you specify a size of size 200, then uh, you get 200 time steps, and then that becomes trained immediately on those 200 time steps.
Sorry, one more time.
So for each call to the environment dot step, it
Mhm.
will return 200 time steps worth of data, and then you train immediately on those 200 time steps. That's what you're saying.
So you still collect you still collect data until the batch is filled up, right? So in other words, the argument of the PPO stays the same. For our implementation, I still have 2048. I just have a batch that say this, right? 2048 until it finishes, and those observations and actions are going to be used for my calculation.
Okay, so basically you can set the vector environment n steps to be 2048, and then
Oh, sorry. Yeah. That would depend, right? If I have, let's say, one environment, then the n steps could be 2048. So in other words, there wouldn't be a batch size anymore. It would be how many environments you want to have and how many n steps you want to take, and
Okay.
the multiplication of them will be your batch size.
Okay, so it's not necessary for the batch size to be equal to n steps.
Beg your pardon?
N steps does not necessarily have to be equal to the batch size then.
No, not at all. It's in fact the multiplication of batch size and the in environments is the batch size. They're related, yeah, directly related, but the n steps is not the batch size. Yeah, so what else was I going to say? Well, technically, this also introduces an additional benefits. We could, so I think that by default, when you just call this function to say, gem.vector.make, I think it's by default synchronously, but you could also set it to be asynchronously. take more CPUs. If your environment is your bottleneck, then by doing this optimization, it'll speed things up a lot. But if your environment is not the bottleneck, it wouldn't make much. It shouldn't make too much difference. So that's sort of the plan that I was hoping to do for PPO and A2C. And something that maybe we should also try to clean up is the SAC implementation. As you can see, SAC performs really poorly in all of the domains we tested. As an example, SAC is over here, right? Reaches around 1200 reward, but that is actually not the case for a lot of the benchmark done by other people. So that's something that I hope to eventually fix. And after we do the Atari for A2C and then the fix for SAC, I think we essentially have a major release will be ready, because all of the implementations will be in a way considered to be high value, high quality, because they've been benchmarked on a variety of different games, and the code is easy to read, so forth and so on. So that's sort of the plan. I encourage you to participate as well. Feel free to download the PPO code and see if you can try it out and see what's the difference between using PPO batch size versus what's the difference between the vector environments and using the batch size. In an essence, in a way, there are three kind of ways you can run the episodes. The first way is just the PPO.py, where you set a fixed episode length, and you just say first step in episode length, I get the observation, the actions, and so on. In PPO2, here we say for steps in my batch size, I'm just going to keep running until the batch is filled. And then if the environment is not done at that point, then we append the last value to the reward as to bootstrap future rewards, because the environment is not done. And now there's this third ways to do this, is to use the vector environment, which, as we discussed, is also different, and in a way allows you to deal with games that has a very long horizon. I was gonna say something, but I kind of forgot. That's about it. That's sort of the plan. Any comments, thoughts?
So one question was, if you use the vectorized environment and in the middle of the batch, the episode terminates, then you're gonna have to iterate through each individual data point in the states and check if whether the episode has been terminated, right, in that particular state.
That I should check if the state is terminated?
Yeah, like if you are saying it, number steps is 5, and if the episode terminates on step number 3, then you have to iterate over each step inside and check if each step the episode has been terminated at each step, right?
Yeah, if the step is not finished, then you should bootstrap the value.
Okay.
Yeah.
No, I mean if it terminates before the total number of steps, like if you're giving n steps as 10, and if the environment terminates somewhere between before 10, so for that particular run, it terminates at step number 6.
Oh, yeah. Oh, okay. I see what you mean. Then the environment will just keep running, right? If the environment early terminates, then it's not a problem, because you know that the environment is truly done, and then you also know that then you can just use how you would calculate the advantages, because the environment is truly done.
Okay, and when you're checking, you have to go and check each individual state, that is each individual step that is returned, and check if it's actually ending. Like in your implementation, right?
I'm sorry, could you repeat that?
To handle this in your implementation, each time you have to go over the individual steps and check if they're actually done. Right.
No. When you do the actual implementation, you just kind of do this, where you say the bootstrap values times 1 minus done's. So
Okay.
this can be handled very cleanly. In other words,
Okay.
you don't have to. Yeah. You don't have to say for each time step is the environment done. If it is done, then I add the. If it's not done, then I add the bootstrap values. But yeah, this 1 minus done's handles the early termination within the episode. If you have, let's say, n steps equal to 10, and then the episode finishes at 6, this 1 minus done will handle the situations with it.
Okay.
Yeah. All right. Definitely a lot of intricate issues, but I think it's definitely worth it to look into them, understand what they mean, and see what can we improve based on it. All right. Does anyone have any sort of last minute comments or questions?
I am looking forward to the pain.
Yeah, well, we'll see. We'll see how that goes.
To what?
To the pain and the suffering.
Oh, yeah, by implementing the Atari Games. Yeah, exactly.
Yeah.
Yeah, no, actually, it would be really worth to try something else. Not Atari, right? Because Atari still is so popular and it's been solved so many times. That's not challenging, but at the same time, you can like find a lot of resources and.
It is actually quite challenging. Yeah, because first of all, as mentioned, not only you have to solve for one game, you have to solve for sort of a bunch of games to make sure your quality is good. But also, it takes a significantly longer time to run. It takes usually a day or two to run, at least with DQN methods. With actor critics, some of them can be really fast. Like if you use asynchronization, I think some of the really fast one can be done within 10 minutes. So
Gotta go fast.
yeah, I gotta go fast. All right, exciting times. Let's keep working on it and see where it leads us. And thanks everyone for coming, and hope you have a great weekend.
Yeah, thank you.
Likewise.
Yeah, have a nice weekend.
You too. Thanks.
Goodbye.
Bye.
Right.